Okay, so this is the first video or lecture for metric space topology. Now, you did not step into a time machine or anything. This is just a re-uploaded video, and I re-uploaded it because I thought I could do things better. So I'm basically just remodeling like the entire way that I'm going to be presenting this series because I didn't like the way I was doing things before. So without further ado, let's just get started. This video will be about least upper bounds, and to start talking about least upper bounds, we need to first understand what we mean by an upper bound. So if we have a set A, which is a subset of the real numbers, then a number C is set to be an upper bound of A if for all x inside of A, C should be greater than or equal to x. So basically this just means that C needs to be greater than or equal to everything that is inside of A. That's all we mean. So don't get confused by these logical symbols. If you've had experience with logic before, then this should be familiar to you and you should have no problem. But if logic is less on your side, then I will try my best to guide you with what I mean by these symbols. Okay, so let's give some examples, shall we? So let's say we have a set A, and this set consists of the numbers 2, 4, and 7. A set can have multiple upper bounds, right? It's not just a special thing which only one number can possess, right? The number C is not unique. It can be a multitude of numbers. So for example, in this case, 10 is an upper bound because 10 is greater than or equal to everything inside of here, right? 10 is greater than 2, obviously. 10 is greater than 4, also obviously. 10 is greater than 7, also obviously. Similarly, the number 12.7 is also considered as an upper bound, and also 100,000, because why not, right? Those are all examples of upper bounds, right? So just remember, an upper bound is not unique. Multiple numbers can be the upper bounds for the same set. 7 itself is also considered an upper bound, right? Because 7 is greater than or equal to 2, 7 is greater than or equal to 4, and 7 is greater than or equal to itself. So 7 counts as an upper bound. So a least upper bound, sometimes abbreviated as LUB, is an upper bound C of A that needs to be lesser than every other upper bound of A. So a least upper bound is basically literally what it says it means. There's nothing more to it. So let's show an example. We'll use the same example as previous, 2, 4, 7. Right, so basically a way you could think about it is if we form a collection of upper bounds for A, for example, 7 is an upper bound, 8 is an upper bound, 12.7 is, 100,000 is, 7.1 is also an upper bound, and etc. We want to ask the question, what is going to be the smallest number in this set, right? What is the smallest number out of all of these? Then that would be the least upper bound, right? This is a collection of upper bounds. You want to find the smallest one, and that smallest one is obviously going to be the least upper bound, right? Nothing special, nothing more to it. That's just the idea, right? So the answer to this intuitively is going to be the number 7. However, we still don't want to just arrive at an answer randomly without any explanation, even if it is intuitively easy to understand. We still want to be able to explain to it step by step in a logical manner. So let's try to do that, shall we? We're going to set up a proof, and we're going to use proof by contradiction. So we're going to show that the least upper bound is not above 7, and we're also going to show that it's not below 7. So if we show that the least upper bound is not above, and we also show that it's not below 7, then the least upper bound must be 7 by a process of elimination. So that's essentially what proof of contradiction is in this case. So 7 is an upper bound, and that is clear. We've already shown that 7 is an upper bound for A. Therefore, anything above 7 cannot be the least upper bound. And this is pretty easy enough, right? So for example, 12.7 cannot be the least upper bound because 7 is an upper bound and 7 is less than 12.7, right? In order for 12.7 to be a least upper bound, it should be lesser than all of these numbers, but it's not lesser than 7. 7 is lesser than it. Therefore, 12.7 cannot be a least upper bound. Similarly, for anything above 7, the same sort of argument applies. Therefore, anything above 7 cannot be a least upper bound. So, check mark given over there. For this one over here, it's going to be a little bit more complicated. With proof by contradiction, we're going to suppose that a least upper bound is below 7, and then we're going to show that that leads to a contradiction. So suppose x is a least upper bound and x is less than 7, right? Then x cannot be an upper bound because it is not greater than or equal to all the elements of A, right? For something to be an upper bound, it has to be greater than everything inside of A. And if this number is less than 7, then it does not satisfy that criteria, right? So if something is less than 7, then it cannot be greater than or equal to all of these. How does this lead to a contradiction? Well, if x is not an upper bound, how can it be a least upper bound, right? So if x is not an upper bound in the first place, then immediately it does not satisfy this definition at all, right? In order for something to be a least upper bound, it needs to be an upper bound, and it needs to be the smallest of all other upper bounds. So this over here is a contradiction. Therefore, we give a check mark over here. And now that these two have been proven, the answer over here is justified. 7 is a least upper bound. Now I want to clarify before we move on that a least upper bound is unique. So whereas a set A can have multiple upper bounds, infinite even, there can only be one least upper bound, and that just makes sense, right? Out of all of these upper bounds, we're just picking one of them to be the least. Alright, with that out of the way, let's continue. We're going to show another example. This example will be the interval from 0 to 1, but it does not include the point 0 and 1. So we can represent it also in this way, if you prefer this notation instead. So anything between 0 and 1, not including 0, not including 1. So what is the least upper bound for this set? Well, an educated guess will give the answer of 1. However, this is still something that we need to prove. So let's get on with it. Right? Same strategy here. We're going to show that it's not greater than 1. We're also going to show that it's not less than 1. Therefore, once we give a tick mark to both of these, this answer over here would be justified. So most of the times the arguments will be the same or similar, right? 1 is an upper bound because clearly 1 is greater than or equal to everything inside of this set. That's just obvious. So anything greater than 1 cannot be the least upper bound. This is the same argument we used here. 7 is an upper bound, so anything above 7 cannot be a least upper bound. So I don't have to explain this point again. The next point, however, is going to be slightly different than this over here, right? So suppose x is less than 1, right? That's just the assumption that we have over here. And we're going to show that this leads to a contradiction, right? But we're going to separate this further into two cases. So if x is less than 1, then either it is less than 0 or it is between 0 and 1. This is going to be a bit confusing, so I'll represent this graphically over here. So if x is less than 1, then x could either be on this red line or it could either be on this green line. And this red over here goes all the way, of course, to negative infinity. So red represents this thing over here, and green represents this thing over here. And we're going to deal with these two cases individually. And we're going to show that both of these just lead to contradictions. Right, so for the red case, clearly, if x is somewhere on the red line, then it's not an upper bound, right? An upper bound has to be greater than everything inside of A. Now, if you think about it, what is A? Well, A is precisely the green line over here, right? And so if you want an upper bound of A, then it has to be somewhere above the green line, so around somewhere over here. So clearly, if x is in the red line, then it's not an upper bound. And again, as we have said, if it's not an upper bound, then it cannot be a least upper bound. Contradiction. So clearly, x cannot be an upper bound, and hence it cannot be a least upper bound. So the green one is going to be a little bit more complicated. It's going to be less clear. And that's because x can be really close to 1. So x could be over here. And when we ask the question of whether or not x can or cannot be an upper bound, it's going to be less obvious this time, right? Because if x is like really close to 1, it should be somewhere over here, and it could be an upper bound. If you think about it, it could be visually greater than like all of this green line over here. So we're going to debunk our visual understanding, our visual perception with rigorous math just in a minute over here. To do that, we're going to pick a number that is between x and 1. So how do we do that? Well, why don't we try adding x and 1 together and dividing it by 2? That will give us straight away a number that is between x and 1. So we're going to relabel this whole thing, the number that is between x and 1, as y. And we're going to make a couple of observations. Observation number 1 is that y is inside of A. And A over here is the interval between 0 and 1. So if you have x, which is somewhere in the green line, could be really close to 1. And if we take the number that is between x and 1, it's still got to be a part of the green line. And you could, if you want, check this inequality rigorously. You could show that x plus 1 divided by 2 is less than 1, and you could solve that inequality, and you will see that it is indeed true. But I won't go so far as to do that. Next, we're going to notice that x is less than y, and that's obvious, right? Y is between x and 1, so x is over here, 1 is over here, y is between, so x has to be less than y. Right, and you could also rigorously prove that if you wanted to. And this tells us that x cannot be an upper bound. Why? Well, in order for x to be an upper bound, it has to be greater than or equal to everything inside of A. And these two statements show that x does not satisfy that criteria, right? Y is a number which is inside of A, but x is not greater than that. X is in fact less than that. So x cannot be an upper bound via these two statements. And that is exactly what we want. If it's not an upper bound, then it cannot be a least upper bound. Therefore, we reach a contradiction. So let's give this thing a check mark as well. And therefore, this thing here is justified. So this, by the way, is an example of C being a least upper bound of A, but C is not inside of A. So in this case, we have 1. 1 is the least upper bound of A, but 1 is not inside of the interval between 0 to 1, because we specifically don't include 0 and we specifically don't include 1. Contrast this to the example above, where we have 7 is a least upper bound, and 7 is inside of A. So a least upper bound can be inside or it can be outside of the set. Here's another example, and this time we'll have the set 0 to 1, another interval, but this time it will be including 0 and including 1. So it will look something like this. So notice we have greater than or equal to this time. This means that 0 and 1 are included. The least upper bound for this, if you were to make an educated guess, would be 1 as well, and it can be proven with more or less the same ideas which we have shown over here, and I'll leave that for you to figure out. And once you have shown that this is indeed true, then this also gives us an example of two different sets which are different. So 0, 1 is different than 0, 1, but they have the same least upper bound. So based on this example, we should not automatically assume that different sets have different least upper bounds. So next I want to show that there is a similar concept known as the lower bound. And similarly, we also have the concept of greatest lower bounds. And this is pretty similar to what upper bounds and least upper bounds are. So a lower bound is basically a number which is less than everything inside of the set. So if we have A over here, a lower bound could be the number 1, or it could be 0, or it could be 2 itself. And similarly, we also have a concept of greatest lower bounds. So you take a collection of lower bounds, just like we did over here, and we're going to ask which is the biggest out of everything inside that set, and that will be the greatest lower bound. Are going to be pretty much the same if you want to show that something is the greatest lower bound. So that's why I'm not going to go into more detail there. I'll leave you to explore these two concepts on your own. And with that, I will end this video. Thanks for watching.